Let's move on to talk about frequency spectrum. Now, we've just gone through how you can represent a signal as a function of time, okay, and obviously this here is a Fourier series. You can represent that as a Fourier series, okay, and this is what's known as a time domain signal, okay. So we've got time as our x-axis and our force as a y-axis. So this is what the signal looks like in terms of time. Now, what you can do is if you take all those, here's that function analytically written, and obviously I could write it as a Fourier series, and it turns out that Bn is 0 because it's an even function. If you saw that you can reflect it around the y-axis, okay, it's symmetrical about this point, so therefore it's an even function. That means the Bn terms are 0. We have only An terms or cosine terms, okay, and we end up with An is this function here. Obviously, depending on n, this could be 0 or not. And what you can do is you can plot those An terms as a function of frequency, okay? Over here we've got n, basically. So obviously here I've got omega 10 and omega 5 and so on. And so for every value of those omegas, okay, omega 1, 2, 3 and so on, I have a value for A of n, okay? So that's like the strength of this frequency that's playing a part in putting together the function. Obviously, when n is 2, omega 2, I get 0, because if you remember it was n pi upon 2, okay? When n is 2, I get 2 pi upon 2. Obviously that's sine of pi is 0. So when n is even, we actually end up with 0. But obviously when n is 1 and 3 and 5 and 7 and 9 and 11 and so on, okay, we get a value. And this is, like I said, this is basically the strength of that frequency that's playing a part in putting together your square wave function in terms of a Fourier series. And this is known as the frequency spectrum, okay? It's in terms of frequency along the bottom, okay? This is slightly incorrect because obviously this value here is n, not n omega. Omega is the fundamental function, so this should actually just be n along the bottom. But obviously I could write omega 1, omega 3, omega 5 and so on if I wanted to actually give you those values at that point there. So that's the frequency spectrum. It's frequency on the bottom, and then the strength of that frequency that's playing a part in putting together your function. So that's the frequency spectrum. This is what's known as a frequency domain response. Now, why is that important? Well, let's think about sound. Okay, sound in physics is actually just a compression of airwaves passing through the air. Okay, and what you hear is basically what happens in your ear is you have these pressure ripples that come into your ear. They vibrate a little bone in your ear, and your brain processes that vibration into a sound that you hear. Okay, so we have essentially a compression of air molecules against time. Now you could plot that. Let's take a specific point. The sound passing through this point, I can measure the pressure ripple. Okay, and that will give me a time domain response, which will be quite random. I'd imagine there's various other sounds we can hear. We can hear the air conditioning. Okay. The computer will be making sound, all that sort of stuff. So there'll be a level of noise behind it. But obviously the sound that you hear, the sound that's coming out of the microphones and stuff, or the speakers, is obviously my voice, and that's passing through this point. And obviously that will be a pressure ripple that will give me a time domain response. Now obviously looking at that time domain response is going to be a mess. It's going to be random. You'll be able to work out what's going on. Okay, and even if I was saying a constant note, so if I was going I'm not going to have a nice sine wave going through that. It's going to be noisy. But what you perceive when I go is a tone, is a certain frequency. Okay, and so what happens is you can convert that time domain function, that mess, into a frequency domain function, and what you hear, what you get for that frequency domain will be that specific frequency. Now, if you think about, I'm sure many of you play musical instruments perhaps, or have done in the past. Obviously, if you're playing a single note through that musical instrument, okay, so let's say you're playing the A above middle C on the piano, okay, that's 440 hertz. Now, if you're playing that same note on a violin, you can tell that it's a different instrument, okay, because it sounds different, okay. but yet the fundamental frequency that when you convert it will be the same thing. Okay, so even if you're in a sound proof room, so the only thing that's actually that's vibrating the air molecules will be that instrument. Okay, the time domain will look different. Okay, because a violin sounds different from a piano, and it's the same thing. If I say ooh, that's different from ah. It's a different shape thing, but it's the same note. Okay, so what happens is that when you convert that time domain to a frequency domain, you'll get the same peak at that certain frequency. Okay, on a guitar and stringed instruments, you'll actually get when you pluck a string on a guitar, you get the fundamental frequency, which is a note you can hear, but within that vibration on the string, you'll get the multiples of that. Okay, so you pluck a string on the guitar, you'll get the main note. But if for example, if you rest your finger at the middle point of that string while it's playing, it'll actually go up an octave because that's the second that's the second harmonic, and so on, and all that sort of stuff. So, but that's waves. We're not going to talk about waves. But like I said, that's what you get. You get the frequency domain function, and that will show you the peaks of the frequency. So with an engineering example, you've got a jet engine attached to a commercial aircraft. Obviously, there's a structure holding the jet engine onto that aircraft. Okay, obviously that jet engine is probably not going to be perfectly balanced. There might be a little bit of oscillation, so the shaft is moving up and down, and obviously that's imparting a force into that structure, which is essentially a spring. Okay, which is attaching the jet engine to the wing of the aircraft. Now, obviously, that excitation force is going to be a certain frequency, dependent upon the engine speed. Okay, but what you need to do is you can look at the structure, and you can shake it randomly. Okay, and that shaking randomly will give you a time domain signal. You convert that to the frequency domain signal, and you get a peak at where its fundamental or its natural frequency is. And what you can do is, once you do that, you can then determine whether the excitation of the jet engine is going to excite your spring, essentially. And obviously, you don't want that excitation force to match your natural frequency of that structure, because then you end up with resonance, and resonance, as we know, is bad. Okay, so that's a sort of example of why you might want to go from the time domain to the frequency domain. Okay. And this happens all over the place. Often you'll want the frequency domain response because tells you a lot more than the time domain response may do so. Okay, this may be really, really noisy. Okay, but within that noise, there's a dominant frequency that you can see from the frequency domain. Now, next semester, when you're doing control, you'll also talk about time domain response and frequency response. Okay. Because it's quite important in terms of control to understand what's going on in terms of frequency as well as the time domain. Okay, so you'll plot responses in terms of, not only will you have the time domain response, which will look like some of the stuff we covered back in chapter 2, where you've got step force and you get damped response and that sort of stuff, but you also look at it in terms of frequency, which will give you the strength of the response in terms of the frequency, and that tells you an awful lot about the control system. But like I said, it's got engineering applications in terms of vibration as well. If you want to test a structure, okay, to make sure that whatever excitation force it's going to experience is not going to hit resonance, then you can do this. You can shake it randomly, okay, and get a time domain response for its vibrations, okay, and obviously then you can convert that to the frequency domain. Now, I've said quite flippantly, just convert it to the frequency domain. Obviously, that's fine if your time domain response is a periodic function. You can convert to the frequency domain just by taking the coefficients of your Fourier series. But often, that's not the case. The Fourier transform, okay, is a certain type of Fourier series in a sense. Well, I lie. A Fourier series is a certain type of Fourier transform, okay? And a Fourier transform allows you to deal with a time domain signal that's of a different form. In fact, any signal. It could be non-periodic, it could be a random signal, or it could be discrete, okay, a measured signal. So say like I said, you've got your component, you're testing it on a shaking table, you've attached an accelerometer to that object to measure the acceleration forces. Obviously, that will give you a time domain response but obviously it's a measured signal. So at a certain frequency, depending on the frequency at which you're measuring the acceleration, okay, you get what's known as a discrete signal. At specific points in time, you've got a value for acceleration. And a Fourier transform can deal with any of these signals, as well as the periodic one, which is what we've done up here, and that's the Fourier series. Like I said, a specific type of Fourier transform. And the whole idea behind the Fourier transform is it transforms from the time domain to the frequency domain. Okay, and you can have inverse Fourier transform, which will convert from the frequency domain back to the time domain. And you get certain shapes will have certain spectrum, and vice versa. And there's various other properties to do with Fourier transforms. And again, if you want to look at the maths and the derivation of the Fourier transform, if you're interested, okay, is in the appendix of your notes in chapter 9. Okay, but like I said, I'm not going to assess you on your ability to apply a Fourier transform to a certain shape. Again, in previous exams, you will see that I've said, what's the frequency spectrum of a square, of a square or something like that, or triangular wave. I'm not going to ask that stuff from this year onwards. Okay, so you can skip those questions if you come across them. But like I said, non-periodic, random, or discrete. Well, let's just take the non-periodic as an example. What you do, essentially, with a non-periodic signal, say we went back to our square wave. Here we know quite clearly that the period is 2 pi. Okay? But what happens if that period started increasing and increased and so on, such that it was approaching infinity? Well, essentially what you're left with is 1 pulse. Okay, that's a non-periodic function. But what happens to the omega as t goes to infinity, or the difference between omega 1 and omega 2? Okay, here we've got quite clearly a discrete difference between omega 1 and omega 2, where omega 2 is 2 times omega 1. But obviously that delta, that difference, is going to reduce, because if you think about the equation for period, that's t equals 2 pi upon omega. Okay, well, if t goes up to infinity, omega must go down to 0. And so what you end up with in terms of a frequency spectrum is you end up with a line, okay, as opposed to specific frequencies at certain points. Like I said, t goes to infinity, the difference between those two frequencies must go down to 0 because of the relationship between t and omega. Okay, and you end up with a non-periodic signal being expressed as a frequency domain response. Okay. Like I said, as t goes to infinity, you get a non-periodic signal, okay, and then obviously you could take the Fourier transform will allow you to take the non-periodic signal in terms of time and get the frequency spectrum or the frequency domain signal. Now, if you're dealing with a discrete signal, you may come across the term fast Fourier transform. And fast Fourier transform is essentially an algorithm that deals with discrete signals. And the reason it's called fast Fourier transform is there's many ways you can apply a Fourier transform to a discrete signal, but the fast Fourier transform is very computationally efficient. Okay, and so often in computing and stuff, when you're dealing with measured signal, perhaps in your final year project, you'll be measuring the acceleration of something. You want to work out the frequency domain. Okay, you'll probably use the fast Fourier transform to get your frequency spectrum from your measured signal. And so as an example, okay, here we've got a measured signal, okay, and this was, I'm not quite sure where it was from, but basically this is my time domain signal. This is a measured signal, so I've got a value up here in terms of amplitude, okay, normalized around 0. I've got sample number. Now, like I said, if this thing is running at, say, 128 hertz, then obviously that represents 1 second, that represents 2 seconds, or so on. I could be running at 32 hertz, 1 second, 2 seconds, 3 seconds. So this is time along the bottom, essentially. But that's in sample number. And what you can do is you can take the fast Fourier transform of this time signal, which gives you no information whatsoever about the frequencies within that signal. You can't look at that and say, oh, I think there's a 60 hertz thing in there and a 26 hertz. You don't know. You can't look at that. Take the fast Fourier transform and a bit of signal conditioning, you get a line like this. Okay? You can see quite clearly that there's a big amplitude at 13 hertz. There's a second harmonic, 26 hertz. There's a third harmonic, 39 hertz. This is probably because the thing was plugged into a mains in the United States, because the mains in the AC current in the United States oscillates at 60 hertz, The reason why I say the US is because in this country it's 50 hertz, but here is 60 hertz, there's a peak there, and you've got this sort of background noise, okay, which is simply, here is white noise, this is called 1/f noise. And like I said, what we've done is we've done a bit of a frequency conditioning, a bit of filtering, because we've basically knocked off any frequencies above 70 hertz. So we've used what's known as a low-pass filter to just look at the lower frequencies. We've ignored the stuff at higher frequencies. Okay, so that's, like I said, it gives you an idea of the way this could be applied. You could take a measured signal, you take the Fourier transform, and you get your frequency spectrum. And like I said, it's quite clear that here we've got 3 different frequencies. Okay, these are obviously quite low frequencies, but like I said, you could do the same thing. You take, this could be a time domain signal of the sound that's being made. Okay, you take that particular point in time, you get a sample number. Okay, particular place, but across a number of seconds, you'll get a sample, an amplitude, and then you, like I said, you take the Fourier transform of that, and you'll get a frequency spectrum, and that's the sound that's being played, like ah or ooh or e, whatever. That will have a different thing, and it will give you your frequency spectrum.